Okay, so I'm gonna be going over M1 Tune. This is one of the two, uh, one of the three software programs that I'm somewhat familiar with from the Motec. There's I2, which Anthony's done a lot of work with, and that's the data analysis part where you look at the the graphs and all the numbers from when you were driving, and you can use that to make improvements in terms of lap time, car diagnostics, that kind of thing. There's M1 Build, which is where you can configure your ECU. You can code in your own functions, and it's kind of their advanced software. This is M1 Tune. This is for tuning the engine. This is like the basic thing that anyone with using a Motec would need to tune their engine. I'm going to be not going through the tuning because I don't have a running engine, but I've gone through and a lot of the setup for the engine. So I'll be showing you all that stuff. So we open the package. That's just whatever file it is. It's this one. Now this package, opening this package opens up a workspace. This is a pre-made workspace, meaning that all these pages and all the different tabs and stuff, they've been set up by, well, we got it straight from Motec when we bought the ECU. But you can make your own. You can make your own workspace and configure it with as many or as few pages as you want, and they're all customizable. So that whole thing, this whole thing is called the workspace. There are different workbooks, so you can make a custom workbook here. They offer that, but then they have a tuning workbook, and they have all these setup workbooks, which is what I'll be going through. So if we went to initial setup, we then have our work pages, which each of these tabs is considered a different work page. And they've just set this up in such a way that it's supposed to be easy to find all the variables that you need to input and configure your engine. So I'm not going to go through everything in great detail. If there's some things that are very important or interesting, then I'll talk about that more. But we'll just start with the basic engine stuff, and I'll go through each of the different work pages. So start with the engine details. In order to figure out how much fuel to put into the engine, it needs to know how much air is going into the engine. And to do that, it needs to know the size of the engine. So that's where you put this in. So it's 0.45 liters, 450 cc engine. Engine run threshold, that's just to distinguish between cranking the engine and it actually running. Because when you're cranking the engine, you supply it with more fuel, typically right off the start, to try to get it to fire up. Because when the engine's totally dry, it doesn't have any fuel sitting in the intake manifold, and it needs an extra boost to get started. These parameters, like this and this, these things, these are basically how the ECU is going to figure out the amount of air going into the engine, using like what sensors and where the sensors are located. So we have a map sensor on the intake manifold. That's basically what this is telling it. It's a single-cylinder engine. This is a technical parameter that I don't totally understand, but you're supposed to have it at about 20 seconds. You also tell it the kind of fuel you're using, because like it says right here, different fuel types will have, where does it say that? No, it doesn't say it here. Different fuel types have different air-fuel ratios. So you need to put in a different amount of fuel for however much air the ECU calculates is going into the engine. So that's why it needs to know. We're going to be using E85, so let's choose that. It's a pretty common fuel, so it's one of the things you can select. And these are things about, again, how it calculates how much air is going into the engine. Right here, this is where you can configure up to 12 cylinders and where they are in the firing order. So you tell it like which bank it's on. So if you had a V12, depending on how you count your cylinders, 1 through 6 could be on one bank, 7 through 12 could be on another bank. You could have even on one bank, odd on one bank. I know Ford and GM use opposite sort of strategies for numbering their cylinders. One does 1 to 4 on one bank, 5 to 8 on the other bank, but that doesn't matter for us because we only have a single cylinder, so it makes it really easy. You have your cylinder 1 bank, and you'll notice there's no place to put in the TDC angle for cylinder 1. That's because it's always assumed to be at 0. That's sort of the starting point. And for us, it's just that easy because it's a single cylinder. So that's it for that page. It gets a little more complicated as we go through. These are the inputs and outputs. So these are major things like sensors that we have. There are digital ins and outs as well. So this is the list that they've given us for sort of the basic ins and outs that you'd often see on cars.
Sorry, Kaden, 1 second.
All right, so there are a lot of inputs and outputs that we are not using, like a lot of these different things. Some we hope to use in the future, others just aren't applicable. For example, you can have 12 different knock sensors on this engine, which you could use for individual cylinder knocking on like a V12, way out of our wheelhouse. There are lots of things for temperatures and pressures. We don't have that many temperature and pressure sensors. Maybe in the future we'll add some across the intake and exhaust, but right now we just don't use them. So some of the ones that we are using, brake pressure, front and rear, we're going to have those sensors on the master cylinders. That's good for data analysis. Clutch pressure, we can have clutch pressure, and actually I think we decided we're not going to use an analog. We'd rather use a digital in for that. So we choose one of the digital ins. We can change it later. I've just been sort of saying it's a digital or an analog for now, and we'll configure exactly which pin that goes to. Again, coolant temperature. Obviously, we need that. This is an output. So I/O stands for input and output. So we need to output to things like the fuel pump and the cooling fan. In the case of the cooling fan, we plan to power it directly from the ECU because we don't expect it to draw much current. I think there's somewhere in the neighborhood of like 7 amps. So this half bridge output, this can go high. I think the half bridge idea is they can go high or low side, so they can supply 12 volts or they can ground the signal. There are other outputs we could use, like we can use these pins that are labeled for the injector. We can use those for just regular inputs and outputs as well. You just have to tell it so. And you can see injector 1 is not available because we're actually using injector 1. But that gives us all these other injector outputs that we could use for other things. They're just modular that way. What's this one? Synchronization. So this is the this basically tells it's a sensor on the engine that tells the ECU how fast the engine's going or where the engine is in its cycle. So that's a critical input that you need, and I've set that to the universal digital in 2, but that might that could change, but that's just one option for where we can put it. Fuel pressure, we have an analog fuel pressure sensor, so we'll be able to track that. The advantage to having an analog fuel pressure sensor is that you can compensate for increases or decreases in fuel pressure as it goes up and down, and you're going to be getting still the correct amount of fuel into the engine. So the ECU has the logic to be able to compensate for varying fuel pressure.
I had another thought too with fuel pressure. We could run the pump straight off the ECU and PWM it if you want to do pressure, and then you can eliminate the manual pressure.
So that's another thing. That's another thing that's possible. I did do a little bit of research on that. The problem with PWMing higher current sources like that is it creates a lot of heat. There are even a dedicated PDM, power distribution module, from Motec was. I saw an example where it was even overheating, trying to power. I think it was a fuel pump. It might have been it was a water pump in that case. But Yeah, so that's something we can definitely look into, but we have to choose the right frequency in order to make sure it doesn't overheat. Hopefully there's a way to do that, because that would be really nice. But as of now, we just have this output to power the fuel pump. Was this going to be, this was going to be a relay, right, Marco, for the fuel pump? I think
Yeah.
I think
That's
we were
what
planning
currently
on
is,
running
yeah.
a fuel relay. But again, that's something that we can change in the future. It'd be really nice to be able to step down the fuel pump and run it at a lower power when we don't need all the fuel. Just saves on like electrical power, which we are, really needing because we don't have a huge stator to generate electricity. That's just the injector, the fuel injector. There's only one of them. Gear position, that is as you change gears, it'll change the voltage at this input. There's a position sensor inside the engine, so that tells the engine which gear it's in, and that does things later. And when we add in the shifting, it needs to know what gear it's in order to know what to do about it. We have gear shift up and down, so these will come from the paddles on the steering wheel. Ignition, just one ignition coil, so that's really easy. We have inlet air temperature. That's again used to calculate how much air is going to the engine, because in order to know the mass of air, you need to know how dense it is, and temperature affects that density. So we can compensate for changes in temperature. And this is the map sensor. So this is the main measure of the load on the engine. If you know the pressure inside the manifold, for the most part, you know how much air is going into the engine. So then you know how much fuel to add in. As you increase the throttle, so as you step on the gas pedal, it opens up the throttle plate and it puts more air into the plenum. It allows it to flow in faster, which creates a greater pressure in the plenum. Typically, the pressure in the plenum will go anywhere down at idle, or when you close the throttle at a reasonably high RPM, it'll be down maybe 20, 30 kPa. Then when you're at full throttle, it should be at about 100 kPa, which is about what the atmosphere is. So knowing that, you know how much air is going into the engine. That's just a tack. We can output a tack to shift lights, basically shift lights, whether that's integrated into a dash or if we have standalone shift lights. The throttle position sensor. So we don't have electronic throttle set up yet on the car. That's something we would like to do soon, but we still need to know the position of the throttle, because that allows us to do things in the ECU. It has a certain logic, whereas when you're at full throttle, this happens. When you're greater than 90%, whatever, you can have tip in and I guess tip out compensations. So as you step on the throttle really fast, it needs to add fuel faster than it otherwise would, in order to build up fuel on the walls of the port of the engine. That's a bit of a technical thing that I won't get into too much detail on, but basically you need an extra spurt of fuel as you get on the throttle really fast. That's something carburetors do too, like more sort of sports-oriented carburetors. They have a little device when you press on the throttle fast. It actually has a little pump that shoots extra fuel in. But of course, that's something that we control with the ECU. There are a bunch of things for like turbos, turbo wastegate. Then there's wheel speed. So wheel speed we'd really like to have. I haven't put anything in yet because we don't know exactly where we're putting it in, and it's not critical to getting the car going, so we just haven't worried about it much yet. But this is kind of nice how you have the left wheel and the right wheel, but then you also have front drive. So that would be like coming out of the transmission. That's how a speedometer will work in most cars. It measures the speed coming out of the transmission to know how fast you're going, or how fast you're going in theory. And the same thing for the rear left, rear right, and rear drive. So like on a rear-wheel drive car, you'd have the rear drive. If you had an all-wheel drive car with a center differential, then you could have both front drive and rear drive to know if your front wheels are spinning faster than the rear. That has different data analysis applications. You could run that into your traction control settings, that kind of thing. So that this These two, the rear left and rear right, we'll probably use those for traction control once we get those set up. And front left and front right, they can be compared to the rear for traction control and for data analysis. This page is kind of boring. It's just some history. It's just stuff and like sensor things. So the crank sensor on the engine. So that's the sensor that reads there's a reluctor wheel on the crankshaft of the engine, and the sensor is able to pick up like how fast the engine is spinning and where the engine is like angularly. So it knows what stroke the engine's on. I'll show you a picture of that for reference. It would be something like this, where you have a wheel with a bunch of teeth around it, and it has some sort of designation usually for where like the top dead center is. So either a longer tooth, we have like a long tooth, an extra long tooth on ours, and some have missing teeth. There's not a good, something we call trigger wheels. It's more this kind of thing on our engine. There isn't a good picture of it, but basically that just tells the ECU where the engine is, and the engine's rotating extremely fast, and we have I think 18 teeth on that wheel, so it has to read at a very high frequency. So then you need things that have to do with the like electrical and magnetic characteristics of the sensor in order to make sure it's not malfunctioning. Because if you're getting a wrong tooth count, it's going to mess up the timing of your fuel and your spark and stuff. But this is pretty much just stuff I left default. Debounce, hysteresis, that kind of thing. Right here, the engine speed parameters with that full screen. This is more important. It has an option for the KTM SXF engine, like the trigger wheel, that tells it basically what kind of wheel it is, telling it that it's got the one long tooth, and we tell it has 18 teeth total. This is a very critical number. If this isn't right, your whole timing of everything's going to be off. We have to tune this, so this is something that we have to measure on the engine and set. So I don't have, that's probably not the final number, but this basically tells where top dead center is, like when the piston is at the top of its stroke, and that's in reference to the long tooth, the one of 18 that's extra long. There are other parameters. If you go function F1, it gives you basically the info for pretty much any of these on what it does. So that was very helpful for me in tuning these, like engine speed reference blank ratio. Like that doesn't mean a whole lot to me, but that it tells you sort of what it does here. I don't need to go into all those boring details, but that would be what you have to read and figure out if you're setting up a new engine. So it's stuff about the teeth on the reluctor wheel, falling edge. So it counts a trigger when the sensor sees a gap. This is supposed to be 0 volts for this application, but that's just sensor stuff. You can also see on all these pages, it has these sort of real-time plots on most of them. When the engine's running, these travel across, and you get similar to what you'd see in like i2 or something. Any sort of data analysis software, you get the plots of what's happening. These are in real time, and they just choose these parameters that are relevant to this page. So again, like critical sensors, they have the critical sensors over here. So if the engine's running and you're looking at it, you can make sure everything's in order. The critical sensors include coolant temp, air temp, air pressure, and throttle position. So I sort of went all over these earlier in the ECU in and outs, but coolant temperature you have to know, so you put in the type of sensor you're using. This was just default. I don't know exactly what the sensor is, but we could figure that out easily. And it knows basically what voltage means what temperature based on the type of sensor. this diagnostic delays, they're on a lot of these sensors, and it basically says if the signal goes weird, like outside its normal range for this amount of time, it brings up a fault. So I said 100 milliseconds. That's plenty long. It's an analog sensor. It should be continuously streaming out a certain voltage. If it's bad for 100 milliseconds, there's something off. Their filters, and these are 5-volt sensors typically. So basically all sensors like that are run off of a 5-volt system that we have on the car. We get 5 volts out of the ECU, and we use that to power these sensors. The reason it says A here is there are 3 different 5-volt channels on the ECU, A, B, and C, and that allows you to split up your sensors between the 3. The advantage, as far as I can see, to having 3 different channels instead of just one big one, one, it's easier to make in the ECU, having 3, that output 5 amps, 2 amps. It's just a sensor, so it doesn't output a lot of current, even if it's powering many sensors. But also, if one goes awry, if something goes wrong with one of the circuits, you don't lose all of your sensors. You only lose the ones that are on that channel. So we can choose A, B, and C. By default, the inlet air was set to B. This was set to A. The map sensors pressure, and throttle position is on. Where is it? Oh, it's a different. It's a different thing. But those are basically the super critical sensors you need. This is something interesting where it says Q. So when you're calibrating your throttle position sensor, it has to know mechanically, like depending on your mechanical setup, it'll have a starting point of a certain voltage, and when you floor it, it'll have a different voltage. So there's a little, like I think a wizard that takes you through it basically. To calibrate these two, and Q in the Motec software is like the key that says calibrate now, calibrate according to current conditions. So you can use that for lots of different things, and I'll get into that briefly near the end. They're optional sensors, so these are additional things, and you can. These are the ones that they provide you with here for airbox pressure. We're not using airbox pressure. We're not using ambient pressure. As of now, we just have the map. Fuel temperature, we don't have that. That's something we should probably add. Fuel pressure, we're assuming a fuel pressure of 400 kPa. Oh wait, set fuel pressure. The value of the sensor would read. Yeah, so that's basically what we set our regulator to. It's somewhere around 400 kPa, which is like 50-something psi. Some other stuff about the fuel pressure sensor, because when you click, like say it's in use, it brings up all these different parameters so you can calibrate the sensors, like tell it sort of what voltage means what. Fuel composition is a yeah, it just tells you. It doesn't give you much info, but you can run like flex fuels, different types of different fuels in cars. That's something that people will do to make more power. If they're going to the racetrack or something, you had a race gas, or you had ethanol or methanol or whatever. We're just going to run the 85 all the time, so we don't worry about that. I wonder if there are any sensors we use here. Brake pressure, again, this is sort of redundant because we went through the ECU input and output. It's like this line is redundant, but this is where you tell it like what the sensor is doing, what everything means in terms of voltages, and this is something that you set up when you know exactly what sensor you're using. We just haven't set up those sensors specifically yet, but that's something we'll do when we go work on the car again. This means it's invalid, like you can't do that. You have to put some parameter here, but again, I don't know what to put there yet. Yeah, I have to do more research on that. But these are mostly just sort of boring sensors. You have the gear position, but we already had that. Ignition. So our ignition's pretty simple, being just a single cylinder with a coil near plug setup. So you tell it basically how much current and the timing and stuff to power the ignition coil with. There's science behind this, and there's stuff that you have to sort of know about your coil, the coil pack you use. That just comes as data from the manufacturer, and again, we tell it it's on ignition 1 pin, and that leaves all these other pins open. So we could use them for something else if we wanted to, having just a single cylinder engine. This is ignition cut. So ignition cuts are a little more complicated with multi-cylinder engines. Ignition cuts are typically something you want to avoid. That's where it just doesn't spark and it lets all the fuel go into the exhaust along with the air, which has the oxygen in it. This is often done with two-step. If you hear a car with really noisy two-step, shooting fire and stuff, most drag cars will do this to build up boost on the line. They spin up their turbo. It's really good at that. Problem is it's super hard on engines. Some engines are not built for it. In general, you want to avoid ignition cuts if you can, and I've done that in the rev limiter tab, which we'll get to soon. But this just tells it if you have a multi-cylinder engine, it has to it cuts different cylinders at different times and stuff. So that's something you can configure. This is the same engine speed reference. You can test your timing. So ideally, you have a timing light, and you can see what your timing actually is, your ignition timing, compared to what it says it is on the computer, and that's how you can tune in this number. So if your timing light's reading 8 degrees, but you've set your test timing to 10 degrees, it's supposed to be 10 degrees. So obviously you're 2 degrees off with this, or something else is wrong. But typically, you would tune this in, and you can just output a couple different things for testing purposes. The injectors. So this is really critical because by knowing what type of injector you have, the ECU can figure out how long it needs to power that injector to get however much fuel it wants to into the engine. So a bunch of the things we've been setting up, actually most of the things you set up in the ECU, tell the engine how much air is going into it right now. And it uses that amount, that number, to figure out how much fuel to put in based on your air-fuel ratio, or what air-fuel ratio you want. And if it knows the type of injector, and it knows like the fuel pressure behind it, stuff like that, and knows your battery voltage, it can tell it how long to power that injector in order to get the right amount of fuel in. But all injectors are different. So there's a big list of different injectors that you can use. And we will just select, again, I think this is just the default. We do know what injector it is, I just don't have it here. So that's something you choose. There are things about secondary injectors. We're not using a secondary injector, but if we were, we could configure it here. We just have the one fuel injector. And yeah, again, the output, it gives you another place to choose the output. It's sort of redundant, but it makes sure you get it. And injectors 2 through 12 are not being used. You can have a secondary output for each one as well. You see, if you choose that, it gives you the option to add a secondary injector. So that's good for stage injection, very high-powered engines. Also, if you want to run 2 different types of fuel, one way to do it is to run one type of fuel to one set of injectors and another type to another set of injectors. That makes it so you can switch between fuel types instantly. So you can run on your regular gasoline for normal cruising. If you floor it, it immediately starts shooting in, an ethanol-based fuel or whatever to make more power. Outputs, this is very similar to the ECU in-out that we were looking at before, but this is where you can program in the things, kind of like what Marco was talking about earlier with the PWM coolant fan. So we're saying it's just on this output, and this is when it turns on and when it turns off. So you can give it a frequency, a PWM frequency, all the way from 0 hertz up to 20,000. Realistically, if we do this, we'd probably set it to oh, maybe a couple hertz. If you set when you set the frequency kind of high, if you have it at 100 hertz, 200 hertz, that's where it creates a lot of heat. But if you have it at a really low frequency, I don't believe it creates as much heat. That's something you've got to do more research on. But you can PWM things up to 20,000 hertz, which is a lot. Not sure what you'd use that for, but I'm sure there are applications for it. That's just to get the right amount of cooling. You can also say, it turns on at 95. Then if it falls below 93, that's what this number means. Falls below this, then it turns off. And that's how you keep your engine operating at the temperature you want. 95 is a little high. I just don't want to overstress the electrical system. Of course, it's more important to keep the engine healthy. It's not unreasonable. 95 is a reasonable temperature to be operating at. Air conditioner. Oh, so this is just a thing road cars do. Typically, when you turn on the AC, it automatically turns on this fan. That just gets you max performance out of your AC. Even if you don't need that extra cooling to cool the engine coolant, it's the same fan that cools the AC condenser. So that's just a detail, for road cars. This ECU does a wide variety of things. I can also tell it the fan to just turn off over 50K, and there's a hysteresis. So then if it falls below 40, it comes back on. That's because after a certain speed, it's not terribly useful, and we don't want to be using it unnecessarily because our electrical system is quite stressed as it is. So above 50K, that's a sort of an estimate for now. We can tune this in, but it should have enough airflow to keep the car cool just fine. And we're looking for an average speed of about 50 kilometers an hour in endurance. So that means hopefully half the time, even if we're at a pretty high temperature, half the time the fan would be off, which would be nice. You can have another coolant fan that does that. Fuel pump, this is where we can set our, we can output to the fuel pump directly from the ECU or through a relay. And you can test it. You prime it, so when you turn the car on, you can prime the fuel pump. I just set it to 1 second. That's plenty. We have a return style fuel system. It refills very quickly. What was this? Oh, this is just when you shut the engine off. A tenth of a second later, it'll turn the fuel pump off. This is another safety sort of diagnostic thing. If the current is below this value, yeah. So basically, if it tries to power the fuel pump and it realizes there's less than 200 milliamps going through it, it tells you something's wrong because the fuel pump should definitely be drawing more than that. It says right here, the setting is only applicable when the output pin is on a peak volt injector. So that's something we can do. Right now I have it on a half bridge output, but we can just as easily put it on an injector output.
How's it going to know its current output if it's through a relay, though?
It doesn't. So did I set this? It might have been default, but this is only used if we put it on one of the injector pins, okay, and we power directly from that. I figured I'd leave it at 0.2 just in case we do it. It's one less thing to worry about in the future. But yeah, that's totally true. Even if it's going through a relay, actually, no, I remember doing this. The reason I made it 0.2, not 0.5, which is the max here, is because if it's going through a relay, it still draws some current. Going through a relay, if it's drawing less than 0.2 amps, then there's probably something wrong with the relay circuit.
So it might draw a bit less because initially it'll spike up to 0.5, but then it'll taper down probably to 100 maybe.
Our relays
might want to look into it.
20, yeah, I thought they were 20, 30 ohms, so it should draw.
Oh, I haven't measured them.
Okay, it should, yeah. Yeah, we'll see how much, but 0.2 amps is not unreasonable. We can reduce that if necessary. Then there's just the same diagnostic. If the signal goes bad for a certain amount of time, it throws an error. There's a voltage thing and voltage. So you can have a warning light for that. Is this for just the fuel pump? You can have a warning light for pretty much anything. But you can also run that through a dash or just straight to your computer. If you have telemetry going or something, that would be super nice. Not something we've set up yet, but you can get your warnings to that. This tab is super critical. This is your speed limit, so your rev limit on the engine. You basically tell it what the rev limit is. What is this? 9,000. Yeah, let's have it set to 9,000 all the way across there. We're probably going to run our engine typically at an 11,000 RPM rev limit. I just have it to 9 for now. That's a reasonable place to start it. Now this is where it gets kind of complicated. I'll make this part full screen. Engine speed limit. Okay, so this is 5,000 RPM. So right now, overriding that 9,000 RPM is a 5,000 RPM rev limit. That I've just set for when we're first starting at the engine. We don't want, if something goes wrong, we don't want it skyrocketing over 5,000 RPM, especially when it's cold and we don't know if the oil's good and stuff like that. So I've set it to 5,000. This is with the driver switch. So you can have a driver switch that just switches the rev limit for in race mode or extra power mode, whatever, and you can tell it which switch you want there. So Motec has these inputs that are designed to be driver switches, rotary switches, just right toggle switches. You can have like them buttons as well, and that's to change the engine parameters. You see they used to do that a lot in Formula One, to change like the tune and stuff, get more or less power, qualifying mode, race mode, that kind of thing. They've recently implemented rules that kind of limit that, but yeah, this would be like all the switches you have on the steering wheel and stuff on the dash. And where's this? Yeah. So these three numbers are basically what happens as you approach the rev limit. Because to stop the engine, you can either cut fuel or you can cut ignition, or you can do both. Like I said before, we don't really want to cut ignition because then you get big explosions of gas in the exhaust, and it puts a lot of stress on the mostly the valve train, the exhaust side valve train, and breaking that would be super bad. So what these graphs tell you, you can always look at them later. There's stuff like this online too, I'm sure, but basically tells you when you set these numbers to whatever, positive or negative. This is how, as you increase in RPM, what happens. So I have it set engine speed limit fuel margin less than 0. So yeah, this is less than 0. It's negative 200. So I have it as it approaches the rev limit. It will start cutting fuel up until this point. And that's over a range of 200 RPM. And engine speed limit ignition, that would be, well, it has the ignition range, so 100 RPM. So if it keeps climbing over the next 100 RPM, it starts to cut ignition in case something goes wrong and the fuel doesn't slow it down. But at that point, it shouldn't be getting fuel. So an ignition cut is not expected to damage the engine. And even if it does cause explosions in the exhaust, cutting that happening is better than over revving your engine and breaking the connecting rod or something, floating a valve. That's also super bad. So it basically, yeah, these numbers tell you when to start cutting fuel, when to start cutting your spark, and you can do different things. Like if you have it, you can have it cut ignition first before it starts cutting fuel. That'll make it sound cool, but it's harder on the engine. So that would be if I set this to a positive number. That's something guys at High Performance Academy on YouTube talked about. He's talked about that in a lot of different videos. They had one scenario where they switched engines, and they were using the software, they're using a Motec, and he forgot to change it from an ignition cut based rev limit to a fuel cut based rev limit. Which is what we have, where it does the fuel cut first, and they ended up pretty badly damaging their engine just because he missed that parameter. So something super important. There's there are warnings. So if you go into coolant temp warning, which is I set that on another page. We already went through it. Like, what's the safe coolant temperature? But if it's above a certain amount for a certain time, basically it'll set the rev limit down to 8,000. Two reasons for that. One, because you'll be making less power, less friction. There's less heat going into the engine. So if it's overheating, lowering the engine speed is a good way to cool it down. The other thing is it'll definitely make the driver know that there's something wrong if all of a sudden it starts not revving as high. So that's a good measure that we want. There's also engine speed. So if the engine's over revving for any reason, if something goes wrong with our shifting system and we're motoring our engine super fast by being in too low a gear, or something goes wrong with the rev limit, it'll temporarily pull the engine down to a lower speed, or at least attempt to. And same thing for oil pressure. We do have an oil pressure sensor on the car, which is new for us, having an analog oil pressure sensor. And if it drops below a certain range, there's a graph for that later in the software. It'll limit your engine speed as well. 9,000, that seems kind of high for an oil pressure warning. So that's 8,000. Just so that the driver, it's not necessarily to like stop the car from running or save the engine. It's also to make sure the driver knows that something is wrong. But you don't want to be revving all the way up to 11,000 RPM with poor oil pressure, definitely. And this is, as the coolant increases in temperature, you can like lower the rev limit. So that's another thing in addition to this like sort of discrete on-off warning. But that's something I haven't set up at this point. Okay. At the end of most of these workbooks that Motec has provided us with in their default workspace, they just have an all calibrate. It's where you get all the different parameters. So you can display it as a tree or just all of them. And that's basically, this is all the stuff that we went through. It's just not categorized quite as neatly. You can see there are lots of different parameters, and we've already gone through all these in the other work pages. So that was the most boring workbook. I'll get into some of these as well. There's the stuff about CAN. This ECU can support up to 3 CAN buses. That's the system by which the car can communicate with other devices. It uses a digital signal flowing through the 2 twisted pair wires that sort of branch out throughout the whole car. That's a topic for another day. There's a lot of info on CAN, and that's more related to the electrical subsection. But it runs at up to a megabit per second speed. You can choose to make it run at lower bit rates if you want. Exhaust lambda. So that's basically just saying, put lambda over the first CAN bus. That stuff's not too interesting. That's just lambda info. More lambda info. It's not really applicable to us. So this is if you have 2 banks of cylinder. 2. I guess you could have more. Maybe it probably only supports 2 banks, like a V configuration engine, or even an inline, like an inline 6 with 2 separated exhaust manifolds. Then you can configure that, like the lambdas on them, because if you have different air-fuel ratios between your banks, you can compensate for that, like add or take away fuel from one more than the other to maintain the correct air-fuel ratio across your cylinders. This is just the throttle pedal sensor if we used it. So if I set it to there, you can see there are a whole bunch of different things to calibrate. This is for electronic throttle. So there's a bunch of stuff in the FSA rules about this as well. And that's how it's all stuff about how the ECU knows how much throttle you want and what to do if the throttle starts going wonky. if you have a bad signal, if there's interference or a bad connection, the throttle will start behaving not like it's supposed to, and the sensors on your pedal and on your throttle, like the actual throttle body, if they don't match, it goes into error mode and it closes the throttle, stuff like that. So that's what we'll have to set up when we go to electronic throttle, which is something that's super exciting, but also kind of a pain, because as you can see, this page about this servo that controls the throttle, this other page about the servo, this is for bank 2, so this wouldn't be applicable to us because we only have one cylinder. And this is all have to be configured. So there are lots of different things about the throttle, and it allows your engine to like idle better. It allows you to blip the throttle on downshifts or upshifts if you're off power, which is another thing that actually we'll get to in a sec. But electronic throttle is really good. It takes a lot of setup in the ECU. There's boost. We don't have a turbo. Even if you had, I guess you could use it with a supercharger as well for like a wastegate style control. There's cam control if you have variable cams, which again we don't. But a lot of cars have that. Many modern cars have that. Just another cam control for intake and exhaust. They're often controlled separately. Some cars will have only intake, only exhaust. The most sort of the most famous type of cam control is Honda's VTEC. That's binary. That's on and off. But a lot of cars will have variable cam timing. Ford Coyote, even mine, like the 300ZX, my car has that. A lot of different. It's good for both emissions and making power across the power band, because you want your cams to be more advanced or retarded depending on how fast the engine is spinning. It has to do with the air going into the engine. This is the map setup. So the map sensor, so that measures the pressure in the intake manifold, how much air is going into the engine. Just some logging stuff. Again, not terribly interesting. It's stuff you make sure is right when you set up the engine, but not interesting enough for a presentation. This is a lot of the sort of higher level logic stuff. So again, idle control. If you have an electronic throttle, it can control your idle speed. It can sort of fluctuate, open and closed, small amounts to keep your engine spinning exactly as fast as you want it to. Idling. Oh yeah. So there are a bunch of little things. Like when you start the engine, it plays with the idle a bit. You can have idle activate. So yeah. Oh yeah. It's stuff about if the RPM is within a certain range, it decides it's idling or it's not idling. More than 3%, or it has a whole bunch of stuff about ramping into the idle. So if you're in neutral, you rev the engine, you level the throttle, it doesn't just drop right back down to its idle speed. It sort of slowly decays once it gets close, stuff like that. So that's something that we'll be setting up with electronic throttle, but not right now. Idle switch, I believe that's just for if you want to run a higher idle, you can change your idle speed with a driver input, or you can have it. You can see analog ins. Not like you can have different parameters that'll change your idle speed, like when the coolant temp is low. But there are other ways to do that. This is the ignition control for idling. Again, more applicable when you have electronic throttle, but ignition, like we can still control ignition at idle. Again, not terribly interesting stuff. It's how the ignition comes, increases or decreases the timing when you're at idle, because you don't want it to be super rough. You want it to be more smooth, so your engine idles smoothly, doesn't surge and doesn't go all crazy, misfire, that kind of thing. It's just to smooth out a whole bunch of stuff. This would be an idle actuator. So like a car, like a lot of old cars will have a dedicated idle actuator instead of throttle, just like their electronic throttle. So you could, this is something that we could add. We're not planning on it, but it'd be to let, it's a little valve that lets more or less air into the intake manifold that sort of bypasses the throttle to control it. So you can have a cable throttle, but an idle actuator that's able to supply some air to keep your engine going and control the speed. So all cable-driven throttle cars that are somewhat modern will have this. Closed loop fuel. This is more of a diagnostic thing because you set the closed loop, like the fuel stuff is in tuning. So this is just to look at it. Overrun. This overrun is when you're off the throttle and your car's inertia is powering the engine. So you're just like your engine braking, you're slowing down, and basically this is to tell it, stop putting fuel into the engine. That's enabled. When you're off the throttle and you're decelerating, so you don't want to be dumping fuel and wasting it. When it's about, if it's about 1500 RPM, it'll do this. Then it'll start to ramp back into more of an idle control. After that, it'll start just running normally once it drops below that. And this is something you can notice definitely if you have a manual transmission car. If you just put it pretty much any gear, second or third is the easiest. First is kind of jerky, and you just, so you put it in second, you're going 30 kilometers an hour, so you're at 2000 RPM, and you let off. And as you decelerate, you'll notice you slow down, but then all of a sudden it starts bucking a bit, and you get a bit of power from the engine. The speed will go up, and it'll go down, it'll go up, and it'll go down. It'll sort of sit usually around 1300 RPM, depending on your temperature, if the engine's warm or not. So all cars do that, and that's to keep it from stalling out. It has stuff about how to advance and retard the ignition as you come in and out of overrun. So as you get on and off the gas, again, you want it to be somewhat smooth. You don't want to slam into a whole bunch of ignition timing and shock the car, shock the drivetrain and stuff. It's to smooth it out. IETs, intake air temperature. So different ways of is calculating how much air is going to the engine if you know the temperature. So it's stuff about how it filters the data coming in. Those two things are. There's a correction factor. So if your temperature is changing significantly after it goes past the sensor, and you know that, you're able to correct for that kind of thing. Inlet manifold, not in use. It's just different ways of measuring the air temp, basically. We're not using that feature, but you need to know the temperature to know how much air is going into your engine. There are a few more outputs, so we do plan to run some of the outputs to different things at some point, but we don't really need them right now. But you can have various outs to different things when whatever is happening with your engine. It's just very configurable. Multi-exhaust lambda. This is again more of a diagnostic thing. It has CAN stuff, like if you have your lambda, so your air fuel ratio, measured by your oxygen sensors on different CAN buses. And the CAN speed, again, like we saw, it goes up to 1 megabit per second. And more of these real-time graphs, you can monitor it. Exhaust gas temperatures are good sensors to have. You can have them like on all your cylinders if you want. It's not something we have right now. We would like to get exhaust gas temperature at some point. It's not too hard to wire in. It's a good thing to know of engine health. It's more useful when you have multiple cylinders because you can see if there's a difference between different cylinders and exhaust gas temperature. You know there's something off, like one cylinder's getting more or less air, more or less fuel, or there might be another issue. There might be a valve train issue. There might be a ring sealing issue. If you see the temperature in one cylinder is different from other cylinders, but we can't really do that. All we can say is that if it's in a normal range, if it sits at 920 degrees Celsius all the time, we're probably fine. If it spikes up to 1100 every once in a while, that's an issue. That's pretty hot. So we just want it to be consistent, and we'll get that wired in at some point. This would be this is like what my clips had. Not mine, the higher level versions of it, but some cars have variable intakes, so kind of like how VTEC will come on and it changes your valve lift and timing in a Honda engine. You can have a flap that effectively changes your intake runner length to tune for higher or lower RPM, and that can come on at a certain RPM. That'd be how you control that. Flap runner. So you can run, actuators to change the length of your inlet runners. I think there was an FSA team that did that, at least one. It's pretty cool. Kind of complicated, but it's not out of the question. But it's not really something we were planning on doing. But we can easily with this ECU. Turbo speed, important if you have a turbo. Not important if you don't have a turbo. We don't. You hear turbo speed is not measured on every car that has a turbo, but it's especially useful on hill climbs, because as you increase elevation, your turbo doesn't have as much resistance on it, so it spins up faster and faster, and you want to make sure you're not going to overspeed your turbo and damage it. So that's where you really see turbo speed coming in handy. There's alternator stuff. We don't turn the alternator on and off. This is where you can look at different warnings. This is more of a diagnostic thing over here. You can just see if a warning is on, if it's active. You can see, you must enable it and stuff, and that's in the other tabs that we've been through. And it gives you another chance over here to activate these warnings, like oil pressure warning, enabled, and it'll, what does that do? Warning mode, engine oil pressure. I'm not sure if that turns on the warning or just activates it. Anyways, it's not something we're looking at right now, but it's something we can do in the future. Get more warnings in just to keep the car safer. And it's another warnings page for your different things. Knock's a big one. We should get a knock sensor at some point. You don't want your engine to knock. With higher revving engines, like the ones we're using, it's less prevalent. It would have been even less with the Gixxer. With the KTM, knock could be a bit more of an issue. Various things that can cause knock. Basically, if you set your ignition timing a little too aggressively, try to make too much power with it, you can get knock, but you can reduce the chances of knock by lowering your intake air temperature, adding fuel, running richer, that kind of thing. There's another, just all calibrate, before it lists off all the things. Fuel pressure control. So this is something where we can control the fuel pressure more dynamically, and you can have warnings. So if your fuel pressure drops too low, it'll give you a warning or can even shut the car off. The problem with fuel pressure dropping too low is you might not be able to get enough fuel into the engine, and your air fuel ratio will, or your air fuel ratio will increase if you're not getting enough fuel in, and that'll create more heat. If you're running near the stoichiometric air fuel ratio, so 14.7 for gasoline, about 9.8 I think for E85, it creates a lot of heat. You want to run rich when you're at high power to cool things down. It also decreases emissions and stuff. Not that we're worried about that, but yeah, that's a big one. If your fuel pressure drops off unexpectedly and you're at full power, that can be quite bad for your engine. So that's a common warning that we might set up. There are lots of things. So the ECU doesn't just control the engine; it also controls lots of vehicle functions. This is again where we go over wheel speed. You can see the wheel speed front and rear stuff. Rear timeout. Final drive ratio, like this is 3.72. Is that our final drive ratio? Currently, I think we're going to use we're starting with 36 and 13, 2.77. 36 divided by 13, yeah, 2.77. So I guess that 2.77 for our car, and that's something you can change. Basically, they'll just tell it, tell you how fast the car is going, and it can use that for the gearbox control, data acquisition, that kind of thing. Because you can have your wheel speed rear drive, that it goes through the drive, like the transmission output, then through this ratio, then to the wheels. So it'll know there's not something wrong with your drivetrain if you have that set correctly. Front final drive, like we don't power the front wheels on the car, so that's not really relevant to us. Vehicle speeds, you can measure vehicle speeds based off of your wheel speeds or your transmission outputs. And you can also know it based off of what gear you're in and like your engine RPM. There are different ways to get vehicle speed, but that's where you would tell it. This is again what we were talking about, the coolant fan. 50 kilometers an hour, it'll shut off because that's where we've deemed it to be fast enough that the fan isn't helping a whole lot. We have enough airflow through the radiator. The gear stuff is kind of interesting. So we have a sequential transmission. It's a 5-speed sequential. It has that variable, or sort of discretely variable resistor pack. I don't remember what it's called, but it outputs a different voltage, basically. The sensor does, depending on what gear you're in. Neutral is the lowest voltage, and it steps all up until you get into 5th. And so that's why I'm telling it here. The lowest is neutral. If you had reverse, it would be, could be reverse. Gear ratio, gear input. This is between the crankshaft and the clutch. There is a gear ratio. There's like physical spur gears between the two. That's just in the engine. Most cars will have this be 1 because the engine crankshaft goes straight into the transmission output, like just through a shaft. But in our case, it goes through a gear, and that's the ratio of that gear, 2.45 to 1. Output, the counter shaft of the transmission goes straight to the output sprocket, which goes into the final drive, so that's just a 1-to-1. There's no extra gear there like there is on the input. Gear position. This is, again, this Q function where you can set the voltage when you plug it into the car. It'll know, like, when you're in neutral, it's the lowest voltage, and you can press Q and it'll configure that. And there are a couple different numbers here that you have to tune in terms of the voltage, so it knows based on what voltage what gear you're in. Pull up just some stuff about the, making sure it's within a reasonable voltage range. History is this. It's not super interesting. Now this is interesting. Shift actuator. This relates to our new pneumatics on the car, the pneumatic shift actuators, so that we can have paddle shifters. So you output. So this would output to the upshift solenoid. This would output to the downshift solenoid. It's a low. So if we call it low side, that means we're constantly powering the solenoid with 12 volts. Or we're giving it 12 volts, and you ground out that 12 volts in order to power the relay. You could do it either way. The half bridge outputs, I think the point of those is you can do it either high side or low side. If we put it on an injector, it still lets us. Interesting. Anyways, that's how you power the shift up and down. There's a pump. You can have a pump, like if you have an air pump to pump up your air tank to power the shifter. You can do that, but we just have a paintball tank that we leave charged up. Actuator timing. I remember setting this in a different page. I can make that full screen, but there's a whole bunch of info on it. But like when it starts to apply the air, when you press the paddle. Like how long it applies the air for, how long it waits before it'll try to shift again. That's basically what these numbers mean. Yeah. It says driver switches, which we haven't set up at this point, but you can see this tells you basically if it's on or not while the engine's running. AC, we don't need that, but you can turn on the cooling, or the rad fan when you turn AC on. That again. Transmission, we don't have we're not controlling the transmission other than the shifting and the clutch. We don't have fluid pumps that we're controlling electronically and stuff. The transmission's built into the engine. There are the comms, so it has to do with CAN, ADR. We have the different things. I think there's the, it's not on this page, it is the RS232 or whatever it is. Different communication things, RS232, to output info to whatever devices are on your car. I don't know a whole lot about that. Anthony knows more about that stuff, so you can ask him if that's interesting to you. There's just brake and clutch pressures, basically. It can give you a clutch slip because it knows how fast your engine's spinning and it knows how fast your wheels or your output's going, so it can tell you if your clutch is slipping, which is interesting. It can be useful. There's the steering, so we can set up our steering angle sensors. We don't have them right now, but we can set them up. This is all just diagnostics. Again, it's things where they have the Q function. You can look at different things as they go on with the engine, different things that are happening, and it's pretty much all stuff we've been over. It's just this is where you would see it if you wanted to go in and you're having issues. You would go into these diagnostic tabs. Very similarly, monitor is where they give you a whole bunch of different stuff to view what's going on with the engine. Knock levels, you can plot your knock kind of thing. Sensors, if you want just a whole bunch of dials, they've set that up for you. Speeds, you can get your wheel speeds. So that's not something you set up. This is the last thing that I've set up. This race functions workbook. Anti-lag, that's a turbo thing. So we're not using that. Launch is something we can use, but I haven't set it up yet. You can say launch is enabled, and it'll say you have to be under a certain coolant temperature, exhaust temperature, whatever. You press your button, you have a certain input, and it'll put in launch control mode, and it'll try to keep you from blowing the tires off as you accelerate. But that's not something that's critical to get the engine running, and that's not something we should set up right now. Then there's the shifter stuff. So this is has to do with the paddle shifters. Gear shift power on throw position. So there's a whole bunch of stuff. This ECU needs to know what to do based on if you're on or off the throttle, and if you're pressing upshift or downshift, because there are different ways you have to unload the transmission in order to make that shift possible. This is stuff I could spend more time talking about it, but I shouldn't now just because we haven't actually done it, and I don't want to give any false information. I'd like to get this system working before doing a whole seminar on it. But you set things like you can have your automatic system. You have different safety things. Downshiftings particularly safety focused because you don't want to over rev your engine in overrun. Again, more shifting stuff, like you have your throttle blips. When we go to electronic throttle, we'll be able to have this throttle blip to shift gears. Engine speed limit ramp. RPM, 2,000 RPM per second. That seems kind of slow, especially for our engine. Wow. But that's something we'll set up and we'll really tune in once we get the electronic throttle and we get our upshifting and downshifting dialed in. This is the same graph we had before, how it turns the power on to the shift solenoids, and then it shifts. Once it decides that the transmission is unloaded, Like the dogs aren't pressing against each other too hard, then it waits a certain amount of time before it'll try to shift again. There's a nitrous control. Nitrous can get pretty complex. I didn't bring up anything there. But nitrous can get complex. We're not allowed to use an FSE, but that's something you can do on other cars. Bump, that's really a drag car thing. You'll see them bumping up to the line before they take off. That way they can stay on the two-step, build up boost, keep their boost consistent when they launch. So that's a drag racing thing, really. You can set your speed limits. We don't need vehicle speed limits, but you can do that, and you can have it with a switch too, like on a switch. You can do pit control, which is pretty cool. Like they use that in professional racing. You know, you hold the button down, or you have a like a toggle button, and it'll limit your speed to the maximum allowed in the pits, so you can go as fast as possible without going over the speed and getting a penalty. There's stuff about traction, similar to launch control, how you can keep your wheels from spinning too much and coming out of a corner, or when you're going really slowly, if you're in first gear or something, you don't want to lose traction. If it's wet, that kind of thing. Intercooler, you can have like active intercoolers. You can have the water controlled like intercooler pumps to run water through them. That's not something that we use. That's not something that FSE teams would generally use, but has control for that. There's I don't even know what this is. It's race data kind of things, more CAN bus stuff, and again more race data stuff. But it's not really critical to set up the engine. So that's it for the setup. I can show you what this is, but I haven't done any of it. This is just the tuning. So you tune your fuel, ignition. You tune what lambda you want, like what you want your airflow ratio to be. You can see it's always a little under 1. Unless you go to map B, you can switch between the two maps. Where it's more cruising, like fuel efficient, then this is making power. Your flex fuel stuff, which we don't use, boost control we don't use, knock, we don't currently have a knock sensor, but that's something we really like to set up. The engine will knock at different frequencies depending on the engine, and you can have multiple frequencies. That's why you have this range here, and you basically listen for those frequencies with a knock sensor, and you can tell it to look out for those frequencies, and if it gets too strong, then it'll like retard the ignition timing or reduce your rev limit, like we were seeing in the warnings earlier. Knock is a pretty bad thing. It'll destroy an engine quite fast, so that's something to watch out for. Right now, we're not tuning so far on the edge that we're going to be super worried about that, but that is definitely something that we'll use in the future to really optimize the engine. You can ignition trim, so it's modifying your ignition depending on what's going on. Various things, like the overrun, like I was talking about. Ignition timing when you're cranking, set that to 10 degrees before top dead center. Yeah, different trims. For air temp, you change your compensations. That's all stuff you can set up. You can have tables for it. Same with fuel volume. You can change your fuel based off of what's going on with the engine. Like when you're cranking, so Q, it just helps you. Like this is the graph that we have for coolant temperature. How it adds fuel when it's colder, and as it heats up, you can see as you get 0, 20, 30 to 100 Celsius. Like these are all just normal operating temp, 60, 90, 100 even. When it starts getting really hot, you want to add fuel again to try to help cool the engine down. And there's this is just over time and with your coolant temperature. You see engine run time. So if you're doing a hot start or a cold start, it'll give you some extra fuel. But after a minute, it's all leveled out. And if you do a really hot start, it goes pretty much to 0. Because you need a little more fuel. It's harder for the fuel to vaporize when the engine is cold, especially with an ethanol-based fuel. So that's what that table would be for. And there are different tables like that to trim the fuel. Again, camshaft timing. It's cool. Like with your load, your throttle, and your engine speed, you can change the angle of your camshaft continuously, which is pretty awesome. It's not something that we have mechanically on the engine, but we do have the software to control it. Fuel timing is when you spray the fuel into the engine. you can see basically as you increase in RPM, you want to spray at a different time so that you get the amount of fuel you're spraying in that engine cycle is going into the engine. So it more accurately controls the amount of like your air fuel ratio with each cycle of the engine. It's pretty simple. It's just a two-dimensional thing. As you increase in engine speed, the fuel timing changes. This is just their default graph. It's something we might dial in, but this is like, it's a pretty good guess, this graph. I did look at it, and it seems to be a pretty good guess for our setup. This is one of the things I was talking about before with tip-in, how you have a fuel film. You have fuel that basically clings to the inlet port on the engine, like before it goes into the cylinder, and sort of sticks to the walls, like they get wet with fuel. And you can say like, there are 30 microliters of fuel typically on the walls, and if it knows how much is hanging onto it, and you trim it in and out, the fuel film, like minus 50, minus 40, as the engine speed increases, you get more or less fuel clinging to the walls. That tells it. So then as you get on and off the throttle, it knows like how much extra fuel it should be putting in, or how much it should cut fuel in order to keep the right amount of fuel actually mixing with the air and going into the cylinder, because some of it's going to be clinging to the walls. And you can see it changes with coolant temperature and stuff. And you can tune this in. Basically, you set it to 2,000 RPM. I can change this if we wanted to tune it at a higher engine speed, which we'll probably do 3,000 or 4,000 RPM, because it's a pretty high revving engine. And you basically figure out how much fuel clings to the cylinder walls, and the ECU will do all the math in the background to figure out how much fuel to apply on transients. It's on transients when you're getting on and off the throttle that really matters, because there's a bit of a fuel capacity. Just more of the same. Secondary. It's if you have secondary injectors that are further up your intake, they would have a different amount of fuel film clinging to the intake because they have a longer area for the fuel to sit at. So that's all stuff that we'll tune. This is like the most sort of classic tuning table in the ECU. It's just the amount of fuel. So just to think about the Motec ECU being upgraded from our previous PE3, a lot of manufacturers are going to this now. It's called a volumetric efficiency strategy, I guess, way of determining the amount of fuel to put in the engine, or way of determining the pulse width of the injector, technically. This is where you tune in how much air is really going into the engine at any time. So all these things that we've set up are telling it how much air is going into the engine at any time, and we then know what our air fuel ratio should be. So then by measuring it, we can measuring our air fuel ratio, we can see how much air is really going into the engine. So we move these numbers up and down. That's volumetric efficiency. That's how much of the cylinder is being filled, like how much air is going into the engine. And this is the main fuel tuning. The Q function works here too. This is where it's super useful. Like you can, press. It doesn't work. Yeah, I get it. Oh, it's because the engine's not running. Lambda's not going. But basically, you go through these cells. If you get your engine centered on this cell and you really tune in, like exactly what your oxygen sensor is getting a nice consistent reading, you press Q, and it does the math and sets this value to what it needs to be in order to get your air fuel ratio right on your target, which is this table. Like you can see there's a graph. They show it graphically so you can see if there are any weird spots. But this table is what you want your lambda to be, and you use this table to get you to that lambda, basically. So you'd be able to see your lambda here on the live plot. It'll plot it, so then you can see what your lambda is at any given time, and you can adjust for it. So instead of doing the math yourself and typing in the numbers manually, you can go like here, press Q, go up here, press Q, go up here, press Q. Then when you're done your tuning, you can interpolate between them and get a nice smooth line. You can see this graph is pretty smooth. And that'll help you dial in your fuel trims pretty fast. Same thing for ignition. Same table, like same idea with the graphs. There's no air-fuel ratio kind of thing with ignition, but you dial in your ignition, and you can have the two different maps for more or less aggressive ignition depending on what you're trying to do. Anyways, that's the M1 Tune software. That's what we use to tune the engine primarily. I can open up M1 Build just to show you what it is, but I'm not going to go through it. I don't know much about it. And, we don't have that much time, or you probably don't want to sit here for that. But come on, open up. There we go. That's right. Oh, it's crashed. Oh, it's back. All right. There's M1 Build. It allows you to open. Come on. It's a more high-level thing. Anthony and Marco have been looking into it. I know that. This is where you could write your own code for the ECU to run. It's pretty cool. It's like the code behind all the functions that the ECU does. And it's involved with like more advanced ECU setup. So if you have a really specific application, like you have some fancy thing on your car, some fancy system that's not controlled in the parameters that we've gone through, you can make your own firmware to control it. You see where it has all the stuff based off of, calculations, anti-lag, input, launch control. These are all things that it has built into it. These drop downs are complicated. Anthony had a way to get to like actual computer code. But yeah, basically this is the super advanced stuff that you can look into. And it allows you to do more stuff with the ECU, because the ECU is pretty it's almost open source. I don't know, maybe that's not the right term, but you can do a lot of stuff with it. You can program in your own features. So that's just some neat stuff that you can do. And we would really like to get into this in the future and learn how to do more advanced stuff with the ECU. So that's that software, and that would be M1 Tune. So this is what most tuners will use here. If there are any questions, I'm happy to answer them. But that's all I had to present.